Good afternoon, everybody. Welcome to our Hawaii Data Science Institute presentations, Friday presentations. I'm Jason Lee. I'm the co-director of the Data Science Institute, along with Gwen Jacobs. Gwen, say hi. And today I have the distinct pleasure, not just because I'm a huge science fiction space fan, of introducing Karen Meach, who will be speaking to us today. Karen is an astronomer, a real science space scientist, astronomer, astrobiologist, and interim director of the Institute for Astronomy. She did her PhD in planetary physics at MIT, after which she joined us at the Institute for Astronomy. She's won way too many awards, including the Heaps Prize in Physics, the Annie Jump Cannon Award, the Harold C. Urey Prize, and the William Tyler Olcott Distinguished Service Award of the American Association of Variable Star Observers, and many, many awards also from the University of Hawaii at Manoa. In a nutshell, Karen studies whether there is life elsewhere in the universe and uses leftover pieces from our solar system's formation to understand how habitable planets are made. Today, she's going to tell us a bit about her seminal work that she's done in her career, as well as her latest work for comet observation using telescopes around the world, and her efforts towards creating COMA, the Cometary Observation Metadata Archive. Karen, take it away.
Thank you very much. Just one slight correction. I was the interim director, and I have just stepped down for that to becoming now back to an ordinary scientist.
You get to do science again.
As of 1 week, yeah. So, am I sharing? Do you see the screen?
Yep.
No?
Yes.
Oh, yes, okay. All right, well, thank you for the very nice introduction. One caveat, I am not a computer scientist, so some of our team on this project is here to help answer any of the intense computer questions, so that my part will be more focused on the science. But let me start with giving you some big picture questions of why we're engaging in this Cometary Metadata Archive project to begin with. You know, a lot of the big science questions that are driven in astronomy are vetted through a process called a decadal survey, where the entire science community and astronomy gets together and decides what are the really pressing science questions that need to be addressed. And this is done every decade. And then from that, various funding organizations develop their strategic science plans. And in the area of astrobiology, some of the really big picture questions are to really understand the content, origin, and evolution of the solar system, and the potential for life elsewhere, both in our solar system and in other solar systems. And so these are some of the specific areas of study that relate to this within our solar system. It's also a point of national space policy to try and understand the conditions that might support the development of life. So in this context of astrobiology, the real objectives for understanding whether or not you can have life on a planet is to really try to understand the process by which a rocky planet like the Earth forms, and understand both the physics of that process and the chemistry. Now, some of the state-of-the-art telescopes that we have on Earth, including this one, which is the ALMA array in Chile. This is the very best telescope we have that works in effectively the radio wavelengths. And what this can do today is look at regions where stars are forming and get some beautiful images like these, which are showing the very birth phases of a young star, which is in the center. This is an image of the dust, and these dark rings may be where young planets are forming. What we can't do today is see in the region of interest, which is where the rocky planets would be very close to the sun. These units here, since I'm assuming this audience isn't astronomy, astronomical units, 1 AU is the Earth-Sun distance. So we're not yet at the realm where we can resolve this. However, the next generation of these types of telescopes in the decade of the 2030s will have both the resolution to start looking at young planets forming in the zone where the rocky planets form, and it can detect the chemistry. So we will very soon have the ability to make these sorts of observations. Now, very interestingly, as of today, we have nearly 12,000 either exoplanets that are known or exoplanet candidates encompassing over 3,300 planetary systems. And of these systems, there may be 50 planets that could be potentially habitable. And what that means is they're just at the right distance from the star such that they could have liquid water on the surface of the world if there's an atmosphere. So we're on the brink of being able to watch this process elsewhere. But of course, we only have one example of a planet that's habitable and inhabited, and that's ours. So the question is, how do we understand how our planet formed in particular? How did it get the ingredients for life, water, organic compounds? So really the only way to do it, since we don't have a time machine, is to look at the leftover pieces from that formation process, namely the small bodies that never got incorporated into a planet and that have been preserved cold and never heated since the time of the formation of the solar system. And that means comets and icy asteroids. So just as a quick overview of the process of building planets and where these things fall in the timeline, when we start to make a planetary system, it starts with a vast cloud of gas and dust that begins to collapse. And as it collapses, it starts to heat up in the center. It flattens down into a disk. And as that disk gets warmer and warmer and more dust is flowing in towards the star, inside a certain radius in this disk, it will be too warm for ice to exist. So any of the things like water, the ingredients for life, will be in the gas form. Outside of this line, it's so cold that now these things freeze and we have icy grains. And this is called the water line. As things start, as more and more material comes into the solar system, particles start to clump together and they get bigger and bigger till they're meters and then eventually kilometers in scale. And at this stage, they're the building blocks of planets or planetesimals. Eventually, they'll form into both rocky planets and giant planets. And then at the end stages, the gas and dust go away. And a lot of the leftovers that never made it into planethood get kind of kicked out to the outer regions of the solar system. So during this time, a lot is happening in the young solar system. This is a schematic cartoon showing that disk as it's getting flatter, hot in the interior, cold on the outside, and a lot of chemistry is happening because chemistry is very temperature dependent. We also have temperature structure in layers vertically. You'll see a lot of different types of molecules, which will vary as a function of distance from the young star. At the same time as these building blocks of the planets are growing, they're also moving around in the disk. Sometimes they're moving radially, sometimes they're moving vertically. So we're going to get a fingerprint set on these building blocks, depending on where they formed, but they might get moved around later. All right, so what are these primitive things that we would like to look at to try and trace back to the early solar system? The characteristics are you want something small, meaning it's never been heated. It's not big enough to generate heat through radioactive decay on the interior. You'd like it stored in the outermost solar system where it's cold, so it hasn't been heated by the sun. So the types of things people normally call primitive, unaltered. We have meteorites. They've been a bit altered. We can look at the minerals on the inside, and we know they heated enough to have liquid water inside, so they're not entirely primitive. Icy asteroids, I'll talk a little bit about. These are things that are in the asteroid belt. So here's a schematic of our solar system with the sun in the middle. There's the asteroid belt. We see some asteroids that develop comet-like tails. So those are considered primitive. Many comets, and we've observed these both from the ground and in space, and that'll be mostly the focus of this talk. And then some people consider icy moons primitive. Well, they're certainly interesting from the astrobiology point of view. For example, this is the Cassini mission's view of the moon Enceladus around Saturn, where here you can see these plumes of material coming out from a subsurface ocean This probably isn't very primitive because it's been heated and it has a liquid ocean. Then, of course, we have the interstellar visitors. They are giving us the clues of planet formation, but not in our solar system, but from somewhere else. So this is what we're talking about, looking at comets and how they can help us understand habitable worlds. So where does the data come from? Let's take a look at how the data is collected. We're talking here about data that's been collected at various telescopes around the world. And just to give you a feel of how this process works, you would write a proposal to request time on one of these telescopes. Typically, maybe you spend a week writing it. You might hear a few months later whether or not you get a night or two on the telescope. You'll have to get some grant money to travel to the telescope, prepare for the observing and actually go there. Sometimes it's a long trip. Change to a night schedule, and then collect the data. Here's an example where it looks like we might be collecting data in Chile, but in fact, we're all staring at the monitors to see if the weather's going to improve, and we didn't travel several thousand miles just to look at clouds. Nowadays, though, that's not the only way you get data. Sometimes it's a queue process, which means you prepare all the observations weeks in advance, submit them to the telescope, and then the observers at the telescope will execute your program on a conditional basis, depending on what the conditions are. So you don't have to travel, and you probably do get your data without clouds. So the types of data that are usually taken, and I'll show you the ones that we're mostly involved with this data set. Typically, the comet astronomers will either take images, pictures, so big digital images. Here's a nice one with the galaxy. You can get the brightness of an object. You can get the color or how well it reflects light at various wavelengths from the surface. You could get the distribution of dust coming off of a comet, or you can do spectroscopy, which spreads the light out so that we can detect various gaseous species and understand the chemistry of the object. So this is an example at optical wavelengths, and this is an example in the infrared. All of these features here that dip down are actually our atmosphere absorbing light. And once you take that out, these bumps here indicate the various gases that were detected. Now, a lot of you, when you think of comets, you may be picturing some of the beautiful pictures you've seen of comets with these beautiful tails. These are often produced by amateurs with small telescopes or just cameras. On the other hand, the professional astronomer comet pictures look more like these. And just in case it's not dead obvious where the comet is in this image, there it is. So very often we get a very different scale between the amateurs and professionals, a very different scale in brightness and field of view of the images. So ideally, if you're wanting to understand the chemistry and the behavior of a particular comet, you might want to watch it over a long period of time to watch how it brightens as it gets closer to the sun. Because the way the comet works, the sunlight heats the ices, which turn into a gas process called sublimation that pushes dust off, and we see the dust and the reflected light from the surface. So this is images of Comet Tempel 1. You can see not much interesting here. We're showing how far from the sun it is. So this is just inside Jupiter. So we get closer and closer in, you can start to see a little bit of dust. These long streaks here are we've taken a whole bunch of images and stacked them together to simulate the motion of the comet. So those are actually trailed stars. As we get closer and closer, the tail starts to develop. And then as you move away from the sun again, it fades off. There's another example of a comet. This was discovered by Pan-STARRS. And this was actually quite far from the sun. It was beyond the orbit of Saturn, sort of halfway between Saturn and Uranus. And it already has a little bit of a fuzzy cloud of dust around it. We actually found some data in archives approximately 4 years earlier when it was almost out to Neptune. And then we looked at another set of data from the Pan-STARRS telescope. And here we can see the comet at various stages. Now, I know you're probably thinking, that looks imaginary. Why is that the comet and that smudge not the comet or any of the other smudges in the background? It's because this was moving. We had several images side by side, and it moved at the right rate. And as miserable as that image is, that's the comet. So from a couple of decades of ground-based observations and spacecraft observations, what have we learned about comets, and how does this relate to the early solar system? Well, comets are small, small meaning kilometer scale. And here's some images of a comet nucleus. They're very dark. They only reflect a few percent of the sunlight. They're very low density, almost 90% porosity, which means they're very good insulators. And the whole surface isn't outgassing. You can see it's very localized. We have jets coming from subsurface. And in fact, for most comets, only a small fraction of the surface is active. Here's an actual image from the Rosetta mission, really close to the comet's surface. And all this sort of illumination against the black sky is just the scattered light from dust. From the chemical point of view, they're mostly controlled by water ice. There's a lot of other components in comets, including organic compounds. They've seen ices that can only exist at very low temperatures. But what's been puzzling from both the ground-based and space-based observations is we don't see a clear pattern in chemistry saying that we think this group of comets formed here, and that's the expected chemistry. So what we've learned is there's a lot of movement in the early solar system. All of this study, what we don't know really are our big picture questions. What is the original material? How much has it changed? Where do comets form in the solar system? And of course, the big one is, do they play a role in astrobiology? Do they bring material to the Earth, such as water and organic compounds? Well, in recent years, with some of the big surveys ongoing in Hawaii and elsewhere, new types of comets have been discovered that can help us answer some of these questions. But it will be, and this will be something that will be important for having big databases. So let's take a look at the first of these. And this is a discovery made by the Pan-STARRS telescope. This is a big survey telescope on Haleakala. It's surveying the sky with a primary mission right now to hunt for potentially hazardous asteroids that might be on an impact or collision course with the Earth. So in 2013, the PI of the survey came into my office and said, we found a really strange comet. It's on a long period comet orbit, meaning it's coming from the very far reaches of the solar system. It's pretty close to the sun and it doesn't have any tail. Is this unusual? And I said, yeah, because most comets on that type of orbit look like this. This is Comet West. So I said, yeah, that's pretty unusual. So we decided to call these things Manx Comets for the tailless cat. That's a little easier than comet on a long period comet orbit with hardly any tail. So Manx is our term for these things. What was really interesting was when we got some color data. We took a spectrum of the surface. And let me explain this figure because it's an important one. So this is in the visible wavelength region from the blue end to the red. And this is just relative amount of light that's reflected. So this dashed line here represents a particular asteroid type that's found in the main asteroid belt, sort of towards the outer edge. This is the reddest object in the solar system, and things that are red tend to be covered in organic compounds. This gray shaded region represents all the measurements we have of comets, and this is an actual close-up of the Rosetta target with its reddish organic rich surface. And this solid curve here represents inner solar system rocky material, things that were formed much warmer. And when we got a spectrum of our object, it looked like the inner solar system rocky material, which has this absorption somewhere between 0.9 and 1 microns. We said, that's really unusual because it's got a comet tail. How can it be rocky and have ice? And what was exciting about this was it may tell us a little bit about how the solar system is put together. So in fact, if we take a look at this simulation, this represents the Oort cloud that things eventually ended up after solar system formation. This might be our Manx object forming in the inner solar system. It got a little bit too close to Jupiter. It gives it a gravitational kick into the outer solar system. It's heading out to cold storage in the Oort cloud. And this is where all of our long period comets are stored. Eventually, a nearby passing star gets close enough to give it a gravitational nudge into the inner solar system, and this brings in a new long period comet. So we were excited because we thought we finally saw some material that had formed in the inner solar system, perhaps some of the Earth building blocks that could hold a clue to where Earth's water came from. So there was another interesting discovery at about the same time period. This was a little bit later, a few years later. And this was from the meteorite community. And what they had discovered studying a bunch of primitive, unaltered meteorites was that they were exactly the same age, but they had strikingly different chemistry. And the only way they could interpret this was that somehow they were kept separate from each other and they didn't mix in the early solar system. And so their hypothesis was that Jupiter formed really early at about 3 astronomical units from the sun. So over here is one of these beautiful ALMA images of another planetary system showing these gaps. So Jupiter forms early, and what happens is material icy grains typically would drift inwards under the effects of solar radiation pressure. When they reach this region, they feel a pressure bump and they stop. They can't go any further. So you will isolate primitive materials on this side and this side. Eventually, and of course, Earth forms inside Jupiter in the warm disk. So if we couldn't get ices into the inner solar system, where did the water come from? Well, as the giant planets grow, they will eventually be able to gravitationally push around or scatter the bigger building blocks, the kilometer scale objects, and those can go across the gap. So there's a bunch of different models on how the solar system formed from this dynamical migration. Some models, and what's shown here is as a distance from the sun. Again, the Earth is at 1 AU, Jupiter today is at 5 AU. And this is just showing different steps in time with the giant planets growing, and they are scattering or kicking around the planetesimals. Blue colors are icy, red ones are rocky that form in the inner solar system. So some modelers say Jupiter formed right where it is today, but it still kicked around a lot of these planetesimals. We can get water into the inner solar system, but you don't get much inner solar system material outwards. Other models say, no, the giant planets moved around in the disk and then moved back outwards, and then you can scatter the rocky inner solar system material outwards. So either Earth formed in the warm inner disk and somehow got water, maybe from the gas, or it got delivered when Jupiter grew and it came from somewhere in the outer solar system. Where depends on when Jupiter formed and where it formed. But when Jupiter throws things at Earth, it also gets trapped in the asteroid belt. So could we explore things in the asteroid belt, observe those, and get some clues about where Earth got its water? In fact, another discovery that's somewhat recent is the discovery of main belt comets. These are things that are firmly in the asteroid belt. They're not recently captured, yet they have comet tails. And in fact, some of these may be collisions between asteroids, but about a dozen of them get comet tails every time they get a little bit closer to the sun, and that suggests they're driven by water. So these are the things that would be really great to explore from the chemistry and looking at their properties, because they may give us a clue to the early solar system. Unfortunately, they're very faint. They have very little gas because today they're fairly close to the sun and it's kind of warm. So for these, you really want to have a space mission to go explore things in the asteroid belt. So in terms of addressing some of the big picture questions, these 20, 30 years of comet science has given us a lot of detail, but it hasn't answered the big picture questions yet. Missions have the potential to do that, but what most people don't realize is with a space mission, you can't always just pick your favorite target and get there. Usually what happens is they put out a call for proposals and you have an idea for the science and you go to the target that you can get to within cost and within the time frame of the mission. So that means you need to have a lot of information about a lot of potential targets. And that's where big databases will come in, is to help you characterize a potential mission target. So we've got a lot of comet data that's been accumulated. And if we're not going to actually be able to measure gas, if most of this data is imaging data, can we get any information about the chemistry, which is key for the early solar system understanding? And in fact, you can get very rudimentary information about chemistry by looking at how a comet gets brighter and fades as it moves around the sun in its elliptical orbit. It's a little primer on how COMET works. Here's the actual nucleus of the Rosetta target, Churyumov-Gerasimenko. So as the sunlight heats the surface, the ices begin to sublimate, the gas comes off in a flow. The gravity on these is very low, so when it interacts with the dust grain, it lifts it from the surface. And then the comet gets brighter because we see both the reflected sunlight from all the dust, as well as the reflected sunlight from the gas, from the dust and the surface of the nucleus. So of course, how much energy is absorbed depends on how close to the sun, how reflective the surface is, how big it is, how fast it's rotating. But you can compute all of this and compare a model to the actual data. So what's shown here is a set of observations. This was taken over a period of a couple of years, all the colorful points. And this is position along the orbit, where 0 means it's at its closest approach, it's perihelion, and -180 is the farthest approach from the sun. And this is the astronomer's brightness scale and magnitudes, but it's just a logarithmic scale of brightness. So 24 is very faint, you need a really big telescope. So this dashed line just reflects what the bare nucleus brightness should be if it's just brightening because it's getting closer to us and closer to the sun. That doesn't match the data except far from the sun. What if we add water? We add a little bit of water from the nucleus so we have some dust coming off. That's not working very well either. Now we add an ice that sublimates at a much lower temperature, much farther from the sun, adding carbon dioxide, and the data fits beautifully. So this is the way you can get some basic information about the chemistry. So let's take a look at some of the data sources that we have, in addition to the old-fashioned, let's go to the telescope and collect some data. Nowadays, we've got some really big surveys. The Pan-STARRS survey in Hawaiʻi is surveying 1,000 square degrees each night. Atlas survey has 2 telescopes now in Hawaiʻi, and they're installing one in Chile and South Africa this year. And they will survey the entire visible sky every night. And the Assassin survey has 24 telescopes. They're trying to look for exploding stars, but they're going to accidentally capture all these cometary vermin. And so we've got a lot of channels of professional data. In addition, the amateur astronomers are really keen, and they're starting to look at bright comets and measuring their brightness. This is one site, Japanese amateurs collecting a lot of data. And you can see here, this comet is brightening. The red line is just the predicted brightness. Here's the French amateurs. And you see there's a lot of scatter in the data. The Spanish amateurs seem to be really good. They have absolutely superb data. This is all the same comet, by the way. So we're now getting a lot of amateur contributions. And the beauty is the amateurs look at things when they are so bright, they're too bright for the professional telescopes. And in fact, there's been a long legacy of amateurs contributing to science. In fact, the American Association of Variable Star Observers was founded in 1911 because they had a problem with a lot of amateur groups doing their own thing. They weren't coordinated, and the professional astronomers couldn't afford to look at star brightness variations all the time, and they needed to be able to tap into the amateur community who go out and do this every night. So this was formed. It's been very successful, and I actually got my very first astronomy job was to work for the AAVSO. This is what the light curves looked like back then, plotted by hand. And my task was to look at these data points that don't seem to fit, look up in the records, who was the observer, and decide whether I thought it was a good observation or not. Of course, nowadays, this is more automated, and they've got 20 million observations, and you can see the light curves of stars. This one's going from 1910 continuously to the present. And there's nowhere else on Earth you're going to get such spectacular data sets. And of course, now they've got a very nice database-driven system. So why COMA, this Cometary Observation Metadata Archive? Well, like the AAVSO, we have a large set of data that we would now like to explore for these bigger picture questions. This is a cute cartoon that tries to visualize how much data we have. Each line represents the closest a comet orbit gets to the sun, and the farthest, the black points represent data we have on that comet along its orbit. And these different color regimes are different types of orbits. Some comets, we have multiple orbits around the sun where we have data. Each different color represents a different orbital passage. So we have a potential wealth of data now we can model. The problem is that a lot of this data has been on 9-track tapes. We've even got photographic plates that have been digitized. These were converted to exabytes for fear that the 9 tracks were dying, and those were converted to CCD-ROMs. A lot of the records are in notebooks. Some of them are neatly handwritten by myself, but I've had some grad students who didn't understand neat handwriting. So eventually we've migrated to typed logs, but now is the time to get all of this into a database, because if you want to have someone that says, I'd like to study Comet Meech, pull all the CDs that has the data, all the notebooks. I said, I'm not doing it. So that's one of the motivations for the COMA database. Another motivation for this is nowadays, any new funding that you get for astronomy observations requires that you submit data to the National Archives. Well, the National Archive data submission is really quite painful. It's not user-friendly in any way. Querying the data is very awkward. I tried to just query this morning for one comet. It dumps a long list of unrelated data sets, different types by different people. I tried to pull up some data that we had archived there, and it gave a long listing of 163 items that looked like this. When I click on the comet, it gives me this whole tree of files. And if I just wanted a single image of the comet, it would have taken me quite a while, or a massive data download to just get what I want. So COMA is a project that is designed to make it easy to utilize this massive data set and to get through 30 years of comet data to do actual science across multiple epochs of time. So first of all, let me start with the team. I'm the science lead of this. We have Erica and Jacqueline, who are helping with the science use cases, along with Caroline, but she's also helping on the computational side. Jan, Kurt, and Raja are doing the heavy lifting with both the back-end data processing analysis tools, developing the protocols to archive data to the National Archives, and to develop the database architecture. And then we're collaborating with you in the Hawaiʻi Science Data Institute for the user interface and the data visualization. So very roughly, what we would like to do is take the data from the telescopes, do the basic processing, and automatically archive it into the public archives, and then develop a bunch of tools where we can process for higher level data products, bringing in some of the survey data from the professional surveys, as well as the amateur surveys. So with a little bit more technical data, we will be ingesting things into a MySQL COMA database from both the professional and the amateur side. Data will be stored permanently, both locally as well as in the Planetary Data System National Archives. And then we will have a user interface which will interact with the processing science server through JSON communication protocols, and we'll have a very nice graphical user interface for pipeline analysis of the data. I'm not going to go through this next chart in detail, just show you that we've been working hard on the database architecture, and we've pretty much finished this off. It actually started from the Deep Impact mission, where I was one of the team science team members, and my role was to characterize our mission target. And I was getting really tired of the other team members saying, Karen, could you send us some of your data from February? Or could you send us data from 2 years ago? And I'd have to go through the notebooks and CDs. So we started this architecture to enable the team to grab data for one comet. So in terms of the back end of the database, some of the physical processing that's done on the data, Jan has been very diligent about doing a lot of heavy programming to have these ready to interface with our user interface. And I'm not going to go through all of these, but I do want to highlight a few of these. So for example, one of the things that you would like to do from a image of a comet is you want to do photometry, which is effectively extracting the brightness of the object. So here's a schematic example. This is a CCD image zoomed in only on one object. And what you want to do is measure the total brightness of the object. Of course, you need to decide how big an observing aperture to measure the brightness in. You might want to plot to see where the profile of the star or comet actually reaches the sky background. And Jan's tools do this in a variety of ways, but this just visualizes what's happening. Another tool that you might like to do is filtering the images, because when you pull up some of the bright comets, and this is still at a level that is much fainter than most amateurs would be observing, and it's pretty much filling the detector because it's so bright. There's actually a lot of structure in here. And by doing various types of filtering, Laplace filtering, ring median filtering, unsharp masking, you can actually bring out a lot of the details. And when this was first done, this is Comet Hale-Bopp from 1997, I thought, wow, that looks like some biological entity. And in fact, what this is, it's a whole bunch of jets of material coming off of the nucleus. Another type of tool that's very useful is to make isochrones. What this is you can take models of the dust as it leaves the surface of the nucleus, and you can spit off a whole bunch of particle sizes and look at where these grains travel under the influence of solar gravity and solar radiation pressure. Or you can spit out a single set of grains over a period of time and see where they travel. And then that will map out the expected position of the tail, and you can compare it to the comet image. By tweaking these parameters until you match the comet image, you effectively can understand when it started to produce the tail and what are the sizes of the dust grains. You may also want to shift and stack images. Here's just an example. This is probably about 20 images of Comet Tempel 1. And so you can see the comet marching along between the stars. And here it was shifted and stacked so the stars line up, and here it's shifted and stacked just to show the comet. And we were looking to see if there was any tail, and at this point there is not. Now you may notice here, oh, it almost ran into this star. Well, you know, telescope time is very valuable. You do not want to observe the object if it runs into a star, especially if it's a very faint object. So another tool that's been developed by Jan is assisting us with observing planning. You give it a list of objects and how bright they are. And now an automated finder chart is made so that you can compare this to the picture you get off of the telescope. It plots the track of the comet. It also makes an observing plan. At the end of twilight, when you want to start observing, The different colors tell us whether it's close to the zenith where you want to observe, or it's getting too close to the horizon and you don't observe. If it's a solid block of color, everything's great. If there's dots in there, it could be that there's a nearby bright star. It could be that it's passing over a bright star, and that's not when you want to observe. So in terms of the front end design, which is where we're really just starting to get working right now, the idea has been that we will have a very intuitive user interface that's customizable, graphical design where the user can start to query various bits of the data set and apply various functions to produce some sort of desired output. So this is a schematic of how it might work. And now James has started to pull together and play with tools that will actually enable us to start interfacing with the database. Just a more detailed example of some of the use cases, and this is where the scientists on our team are coming in to dream up all of the potential use cases for the group so that we can start the heavy programming. I want to talk just about a couple of ancillary science cases that this database will enable. So let me go back to the old style manual photometry, manual observing, where you go to the telescope and you sit there all night long observing. Well, the light that gets to the telescope has to pass through the atmosphere. And then once it's passed through the atmosphere and it hits the detector, it creates electrons, which is what we measure. But how do we know how many electrons equal a specific brightness? The way you do that is you observe standard stars, stars of a known brightness. And we have to calibrate how much light is lost by going through the atmosphere. Because anytime starlight passes through the atmosphere, it can get absorbed or scattered out of the path. And the more atmosphere it goes through, the more it's scattered. So in the old days, we would observe a whole bunch of standard stars in the twilights, the morning and evening, and observe them at a variety of angles from the zenith. So you go through different path lengths of atmosphere. So here's a plot from a 20-day period in 2009. This is in the red filter. This is in the visual filter. And you can see it's quite stable. And what we're looking at here is how much light is absorbed as a function of path length through atmosphere. And the slope gives us what we call extinction. We don't do that anymore because with the advent of pan-stars, it has observed the entire sky. It has done this exercise, so we know the brightness of all the stars. So nowadays, you just compare to pan-stars and you know the brightness relative to all the stars. But from this older data set, one day I decided to plot the slopes of extinction just on a lark. I thought, okay, it's a little bit messy, but is something wrong with this data? The extinction was huge. What's going on? And I did it in 2 filters and we see the same increase. Now, of course, if you have extra dust in the atmosphere, the light gets blocked. We see this on Mars when there's a Martian dust storm. It gets much darker. You know, here's the case from June to September 2001, a dust storm. So I said, well, was there something happening that put dust in the atmosphere? Looking at some dust measurements in the atmosphere, sure enough, there were dust events at this time. So what happened in 1991 was in fact a massive volcanic eruption, Mount Pinatubo, which put up thousands cubic kilometers of magma, huge amounts of CO2 and aerosols. And in fact, you could even see the haze layers in the atmosphere. And it took a couple of years to go away. So with this data set, we can actually explore dust loading in the atmosphere. And that certainly was not what we took the data for. One final application, a nice advanced application that would be nice to try the experiment. One of the things we did, especially for the space mission, is we look at what we call a rotational light curve. You just look at how the brightness goes up and down as the asteroid or comet is spinning. And so if you had something that was a binary or sort of a bowling pin shape, you would get a light curve like this. Of course, real comets don't look quite so uniform. Here's a bunch of snapshots of comet 67P as it rotated. And if you look at all the complex shadowing on the surface, you can imagine it would be rather difficult to invert an observed light curve and infer the shape here. Well, one of my tasks with both the Deep Impact mission and the follow-on mission was to really understand the rotation of the Deep Impact target, Temple 1. And the reason for this was our experiment was to hit the comet with a piece of the spacecraft, dig a hole, and then as we fly by, measure the interior of the comet to look at the primordial material. While we were successful at hitting the comet, the mission failed because we never got to see the crater. There was too much dust and it took too long for the dust to go away. So with the follow-on mission, the plan was to take another spacecraft 5 years later and fly past the crater and get a look finally and finish the experiment. Well, the comet is rotating. And the thing is, we have to fly past the correct side. We have to fly past the side with the crater. And we had enough rocket fuel that we could adjust our arrival, accelerate or decelerate by about 8 hours. And the rotation period on this comet is about 41 hours. And we have to do it a year in advance, which means we need to know the rotation to about a few seconds precision, which is a huge challenge. Moreover, it was not so easy because here was the observation of the comet. All of these dots here are ground-based observations. So these are perihelions closest to the sun. 1999, it rotated with this period. Then for all of these years up to 2005, it rotated with this period. After 2005, it rotated with this period. It is slowing down. What in the heck is going on? Well, it's likely due to the fact that this is when there's a lot of gas coming off and the jets that are coming out of the comet are acting like rocket thrusters. Okay, we've got to do a prediction with a changing period. Well, when they started to model the data, it's not just a step function. It dips down and comes up, dips down and comes up. And when we were going to observe, the comet was on the upswing. So what happened was they took 15 years of comet data and the team, anytime, here's some sample, this is their model of the rotation. Here's some of the data. Anytime the data didn't fit, they just threw it out. And I kept arguing with them, that is not the way to do science, but we didn't have time to carefully check thousands of data points, so they just threw it out. We used all of the rocket fuel in the burn, and eventually we did pass by the correct side of the comet, so it was successful. But what I think would be spectacular with this now, in hindsight, is we have the data from the mission approach. You could do a really nice neural network study of the rotation and go back into the older data sets and not throw out these and get a really nice model for the rotation. So to summarize, I think with this COMA archive, we are going to have the ability to combine data where we've had traditional types of observing and usage patterns and data sets, but it's now in the context of some really big data sets. And this will give us the potential to start to answer some of these big questions because we can combine everything. Now we're going to have modern all-sky big data surveys such as the Rubin telescope coming online in 2023. We have pan-stars, but these surveys aren't going to last forever. And some of the science we need to do to trace the behavior of a comet along its orbit is going to require decades of observations pulled together. So this is an ambitious project. I think we're well on our way with collaboration with Hawaiʻi data science staff and our teams. I'm really excited to see how this works out. So thank you very much, and I'll take any questions.
If you have any questions, feel free to just have at it. Give yourself a few minutes to think about them.
And Kurt and Jan and Jason are all here. So if it's about the database and the computer science, I'm sure they will be happy to chime in.
So I have a question, Karen.
Yeah.
Just from the standpoint of, I was just thinking about it, looking at your piles of CDs and all that. So as you're working with Kurt and others designing this database, do you tell them all the queries you'd like to make? Is that, how do you provide input to them about how to construct your database so that it works for you?
Well, the queries, you know, that's where we're starting to do the user cases. And, you know, with Jan had designed the strategy of us having the colored full symbols so we can map it out in a way that's sensible for the computer team. So we are meeting to think of every possible use that we might have, and we're also trying to channel other observers, because of course we're designing this so that we can use it, but the intent is that this will be free and open for the entire community.
Awesome. One other follow-up, if I can, I was interested to hear about just how painful it is to upload data into a public repository. Anything you'd like to comment more about that? Why is that so hard, and who's making that so hard?
It's because you have to learn PDS level 4 archiving, and yeah, that's why. If it was just, here's my image, but it's not quite that simple. And of course you have to be very robust. You have to make sure it's completely carefully described. You know, so that part we have to do anyway for the database. But then these archives, when you upload data to the PDS, they're peer reviewed. And so there may be lots of back and forth where the people who have tried to use it find errors. So it's a major pain in the neck. So if we can never have to do that again because it's done automatically straight from the telescope, I will be super happy. As I'm sure many other people will too. And that query where I pulled down some from the database, that level of query is only possible because another astronomer was so frustrated with how you queried the data. So he invented, he calls it a data ferret to go search out data.
That's a great name. That's perfect. Okay, well, you're fighting the good fight on that one. So more power to you, for sure.
But their tools to upload or download fail with big sets. If observer X has one night of data they want to upload or query, no problem. We try and upload a huge set, it crashes. So. You know, not everybody is willing or able to learn the whole PDS-4 architecture because they're busy trying to just do the science. And that tends to mean that people are very reluctant to participate in the archives. Other questions?
So Karen, in that last example you were mentioning where the comet's rotational period was changing and it was losing mass rapidly. What percentage of comets do that to the extent that it becomes very difficult to predict what their standard orbits are? And if so, sort of referring back to Gwen's trailer movie that's coming out in December about comets hitting the Earth, how do we know when something is something we normally expect to see versus, oh, it's something new that we didn't expect that might hit us?
Well, the comets, almost all of them seem to have these, quote, non-gravitational effects because the gas is not coming off uniformly. It's got to create a torque. And in fact, that's how Fred Whipple, you know, back when they were first figuring out what comets were, there was this huge debate. Is it a solid body or is it just a swarm of dust? And Whipple said, because he saw Encke's orbit changing, he said it's got to be a solid body with torques. So anyone that's outgassing unevenly is going to have this. But we can predict it because it seems to be fairly constant. And so with precise measurements of position, we know fairly well how to predict where the comet is going to be over time. The extreme need for the space mission was for us to predict which side of the comet we're going to be passing by a year from now, which meant 1 second or so precision on the rotation period. So that was an extreme need. And in fact, I'm almost embarrassed to say we have hundreds of nights of telescope time just to look at the rotational light curve of one comet. And other people would say, cringe, you got to be solving the origin of the universe or something with that kind of telescope time. But, in fact, that's what's caused all of this controversy over our first interstellar visitor, Oumuamua, because it was just a point of light. You saw some examples in my pictures of a comet that just looks like a point of light. It came from outside the solar system, so we knew it was comet-like. It's basically a building block from another solar system. It did not have any tail. I mean, we stacked tons and tons of images, no dust at all. And we had really stringent limits, like you could have ground up 1 kilogram of dust, spread it over 1,000 kilometers, and we would have seen it, and it just wasn't there. All right, fine. But then we looked at the orbit. We were measuring very precisely the positions. We said, this isn't behaving like it's just being controlled by the sun's gravity. It's actually accelerating. And so in fact, it was accelerating exactly as predicted if it was outgassing. But we didn't see dust, but we had no experiment that could detect the gas. So it could have been outgassing gas. And of course, now you get some of the strange astronomers who say, you didn't see dust, you didn't see gas, it was accelerating, therefore it's an alien spacecraft. But I think that's a huge jump to make. There's valid reasons why we might not have seen dust. If something like this is flying through space for millions of years, if it passes through a cloud of gas and dust, the surface dust could be eroded, in which case when the gas comes off, there's no small dust to push. And we had no experiments that were capable of detecting the gas. So it is not an alien spacecraft, but we did detect its acceleration. And I think it would be really neat to visualize the growth of some of these dust tails in 3D in your lab, or even just try and look at the complex rotational dynamics of some of these in the lab once you solve the rotational state, because it's not just a simple spin, it's complex, it's wobbling.
Yeah, it's a perfect problem to solve with a 3D visualization system.
We're not asking for that in the database, though.
Oh, darn. That was going to be really fun.
Well, you can put it in there. It's just not a requirement.
All right.
Maybe a supplement.
Yeah, there you go. Any more questions? Any last question? We have 1 minute left, 30 seconds left for one more question. Well, with that, I'd like to thank Karen again for taking her time to come talk to us about this really awesome topic, and wish everybody also a safe and happy weekend. And don't look up and go see that Netflix movie in December.